and when should you use them? Now, as I said, it will be high level, and for much more detail, please head over to the Review website and deep dive on database indexing. I'll be sure to link that in the description. Let's get after it. Alright, so before we start talking about indexing, let's understand the problem that indexing solves. So data is arranged in a database in pages. Pages are usually 8 kilobytes of data. And so when you want to find a particular item in your database and you're not using indexing, what happens is that we pull the page into RAM, into memory, we scan through all roughly 100 rows for items, looking for the items that we're after, and if we don't find it, we put that in, pull in the next one, put that one back, pull in the next one, until we eventually find it. And so as you're starting to realize, this is a slow process. To illustrate this, if we had 100 million users in our user table, and each page, as I said, has to be about 100 rows, then that's a million of these pages. Now, each round trip from SSD to RAM is about 100 microseconds. And so that's 100 seconds in the worst case for us to find the item. Worth noting that in reality there's prefetching, there's other database optimizations that would probably actually get this down closer to 3 to 5 seconds. But the point stands, this is far longer than a user wants to wait in order to get a query for some data for a given input ID.
So how do indexes solve this problem for us?
Well, indexes are just data structures that are stored on disk and act as a map to tell us where items or on which page items exist in the database. And so when a new query comes in for a particular item, we first pull that index into memory, check which page that index tells us the resource or the item lives on, and then we pull only that particular page. In this case, maybe it was page 1. And so as opposed to reading up to 1 million pages, as was the case with our sequential or table scan, now we use the index to just tell us exactly which page we should look at. So now naturally the question becomes, well, what types of indexes are there, and when should I use them? Let's start by first explaining what is by far the most popular database index, which is B-tree. And so B-trees are just basic tree structures, just how we learned in data structures and algorithms, where each node in a tree is a sorted list of values with pointers to another page of this, either a child node, is here, or an actual data page, like here. And so to illustrate this with an example, I think it'll make much more sense. So let's say that we had a query like this, where we want to select all users where their age is exactly 51. And in our user table, to do this, we build an index on age. So this is the index on age, indexes or sometimes just algorithms before the indexing called geospatial indexing. And the three most popular and three best known for system design interviews are one geohashing, two quad trees, and three R trees. We're going to really briefly go over each of these. So first off, let's look at geohashing. With geohashing, you take a map of the world, and imagine that's what this is. And we split it into four parts. We label top left 0, then 1, then 2, then 3. Now we can then recursively split each of those cells into the same thing, such that this one is now 2, 0, 2, 1, 2, 2, 2, 3. And by continuing to do this, we get increasing levels of precision, such that maybe the New Mexico area is 31, but Albuquerque specifically is 310. Now, the nice thing is once you've converted latitude and longitude into these one-dimensional strings here, then now all nearby locations share a similar prefix. And so this is Chihuahua, I guess. If we want to find everything near Chihuahua at this degree of precision, then we just get the geohashes near it. 321, 331, 312, and 332, and they all share similar prefixes. And so what we do is we actually weight the geohashes and then just build a B tree on top of the hashes themselves, which allow us to easily do these range queries in the O1 and really O1 with those precise areas. And that's how geohashing works. Now it's worth noting that I did this as just simple numbers for the illustration. We actually base 32 and code them. So for example, Los Angeles, where I'm at, is this, the geohash for Los Angeles. And next up is quadrants. It's pretty similar to geohashing in that we split the world recursively. There are almost some differences. The first is that we map this recursive splitting actually to a tree, not a one-dimensional string. And we only need to go deeper in this tree than where we have points. So let me show you what this means. Imagine this was a map of the world. Each dot is a location in your neighborhood. Say this was yellow. Each dot is a business. And so we split the world into 4 points. We thus create a tree, where the tree has 4 children, and that points to all of the businesses within that grid. So all of the red businesses, all the green businesses is this node, blue and yellow is that. Now you'll notice there's a lot of density in the blue side. And so with quad trees, you specify a K value, which is basically saying that if any cell is greater than K value items, they're recursively split. And so that's the case here. We have more than 5, so we split it again. We come over here, we got another 4 children. And 1, 2, 3, 4. And then one such children, or child, still had more than 5. So we split it again. So 1, 2, 3, 4. Right? And so now when we want to find a particular business, we just work our way down the tree accordingly. And this is the index similar to the B tree that ends up being stored on this. Lastly, we have R trees. R trees are derived from quad trees. They're really similar concepts. But instead of just crudely splitting the world into even 4s, it's a bit more dynamic. It does some clustering in order to find locations or businesses or whatever may be in your database that are close to each other. And then each of these larger groupings can even have a little bit of overlap. And so it's the same general idea. Work down a tree in order to get increasing precision from N, this larger box, to I, this box, and then finally to all the businesses or locations in F. It's just not the case that we need to be subscripting and splitting exactly equals. It's more dynamic and obviously fairly complex and not something we're going into detail in this video. What's important to note as we zoom out and look at all 3 of these strategies is that geohashing is very popular today, and it
là một phần của bệnh viện nếu được. Vậy thì tai nạn của mẹ mình, nên tôi muốn cho các bác sĩ có tay nghề cao hơn, để cho mọi bệnh nhân đều sẽ được điều trị